Welcome to lecture 18, where we discuss a new criterion for the limit of a function, the sequences function criterion. This criterion can be summarized as follows. The limit of a sequence can be used to compute the limit of a function. In other words, if we need to evaluate the limit of a function, we can rely on the limit of a sequence which is somehow related to this function. Let's be more precise. Let f be a function defined in 1 plus infinity. Basically on the part of real line starting at 1 and going to plus infinity, which takes values into R, and this should be a piecewise constant function with pieces of length 1. So this function is defined starting at 1, and in each interval we'll take constant values. For example, in the interval 1, 2, this will be the function, a constant value in this interval, and then in the interval 2, 3 we'll take this value, then in 3, 4 we'll take another value, 4, 5 we'll take another value, and so on and so forth. So this is what a piecewise constant function is, and you see that each piece is of length 1. Now we can think of this function as being defined by a real sequence an. In fact, we can think that in this interval the value that the function takes is nothing else than the first value of a sequence, a1. In the second interval it will take the value a2, in the third interval a3, in the fourth interval a4, and so on and so forth. So in other words, we're saying that if x belongs to the interval 1, 2, we are saying that f of x for each x in that interval, for each of the x's that belong to this interval, the value of the function is given by a1. For x that belongs to the interval 2, 3, the value of the function is a2, and so on and so forth. So in general, we are now rethinking of this function in terms of a sequence. So we can say that we can define a sequence an such that f of x is equal to an for every x that belongs to the interval n plus 1. Well, if this is the case, then the criterion says that the limit of f of x as x goes to plus infinity is equal to the limit as n goes to infinity of an. In other words, if on the left hand side the function converges to a real limit L, so it is of type 1, then also the sequence that we have just defined is of type 1, which will converge exactly to the same limit. If on the left hand side we have a function that will diverge to plus infinity, the same thing happens for the sequence. And if this on the left hand side will diverges to minus infinity, same things happen to the right hand side. And finally, if the function has no limit, then also the sequence has no limit. Okay, so that's the idea, right? So we are basically now led to study a sequence starting from the original function. So we were given a function which was a piecewise function, and we saw that this function is basically nothing else than a sequence. And because we know a lot about the limits of a sequence, this might help. Let's see one example where we can apply this criterion. Let's consider the example 1, where we have the limit as x that goes to plus infinity of an exponential 2 to the x divided by a power x to the 17. We know from lecture 17 that this limit is equal to plus infinity. In fact, we have assumed in lecture 17 that the exponential wins over the power. And now we are going to prove this. Okay, and we want to prove this by using the sequences function criterion, which is to say that we would rely on some sequence of which we know already the limit. And well, in fact, we know that a sequence like 2 to the n divided by n to the 17 will diverge to plus infinity. We know that, okay? We know that the exponential wins over the power if we are dealing with a sequence. So we would like now, in other words, to build out of this sequence that we know, we want to build some kind of function which is a piecewise function f of x, and then we will try to compare this function f of x with the one that is given. Okay, so what we can do now, because we want to prove that this function will diverge to plus infinity, we would like to use the squeeze theorem. So for example, we can write 2 to the x divided by x to the 17. Okay, if we have an inequality like that this is larger than or equal something that goes to plus infinity, we know that by the squeeze theorem this will prove that the term on the left hand side will diverge to plus infinity. So we need now to write something on the right hand side of the inequality which is smaller than the fraction on the left. Now, how can we build a fraction that is smaller? Well, we need the smaller numerator and we need the larger denominator. Okay, now if we assume that we have x that belongs to the generic interval n plus 1, okay, remember what was the idea of the piecewise function. Okay, we saw that if we have n here and n plus 1 here, we know that whatever the sequence is going to be, this sequence basically will take a constant value in this interval, right? But clearly for every x that belongs to that interval, okay, we know that for every x, f of x is going to be equal to a n, right? Good. So clearly for every x that belongs to this interval, we can say that x is going to be larger than n. X is going to be larger than n. But if x is going to be larger than n, then we can replace the numerator with simply 2 to the n, right? Because we know at this point that 2 to the x is going to be larger than 2 to the n. We need to replace the denominator with something which is larger. But you see, clearly in this case, we have that while we see that x is larger than n, we also know that x is going to be less than n plus 1. Then we will replace the denominator with n plus 1 raised to the 17. So we have now an inequality. Now it's all about proving at this point, okay, it's all about proving that this term on the right hand side of the inequality will diverge to plus infinity. So in other words, what we are doing here is the following. We have now this function, okay, let me call this function f of x, okay. This can be thought as a piecewise function, okay, a function that will have in the starting from 1, 2, 3, and 4 will have a behavior like this, okay, because we already know that this will diverge to plus infinity, right? Because this is a sequence where we have an exponential that wins over the power. So this will definitely, we know that this will go to plus infinity, and then by the squeeze theorem, this will go to plus infinity. So, and we are done then. So in other words, we have built a function f of x, and instead this g of x, which is the function on the left hand side, will stay on top of f of x. So if f of x will diverge to plus infinity, g of x will be pushed also to diverge to plus infinity, right? So now as a reminder, we will prove now that f of x, okay, let's prove that f of x diverges, f of x diverges to plus infinity. Remember that we use the ratio criterion to prove this, okay? Let's do this again, okay? We need to find the limit of an plus 1 divided by an. If this limit will tend to plus infinity, or basically to L, which can be something in the interval 1 plus infinity, but can also be plus infinity. If we prove this, then this is a sufficient condition to say that an will diverge to plus infinity. Okay, let's do it. Now remember that we have 2 to the n divided by n plus 1 to the 17, okay? So n plus 1 divided by an is equal to 2 to the n plus 1 divided by n plus 2 to the 17 times n plus 1 to the 17 divided by 2 to the n. And after doing the simplification, we have 2, and then we have n plus 1 divided by n plus 2 to the 17. But of course we know that this will tend to 1, so this limit is 2 is larger than 1, so this proves that an, and which is 2 to the n divided by n plus 1 to the 17, actually diverges to plus infinity, right? So this concludes the proof then. So this is the way how we can use the criterion, okay? Let's review quickly what we have done. We were given this limit, and we don't know how to address the computation of this limit, but we remember then that we know a sequence which is similar to the limit, of which we know that it diverges to plus infinity. So we need now to make a connection between the function, this function, and this sequence. And the way to do this is basically using this inequality. In this inequality, now in this case we wanted to prove that we had already an idea, right, that this function was divergent to plus infinity. So what we have done is building an inequality saying that the function is larger than or equal some sequence, okay? And this sequence has been built by just looking at the numerator and denominator, and then because we know the limit of the sequence, we were able to finally prove that indeed the function will diverge to plus infinity. Okay, so we gave the criterion, but we didn't give the proof. But the proof of the sequence function criterion is quite straightforward, and it is basically remember that we have defined, given the function f of x, what we have done, we have defined a sequence an, okay, that I mean is basically providing all the values that the function is taking in each and every interval if x belongs to n plus 1, right? Now, of course, if an is of type, so this sequence is of type 1, 2, 3, or 4, well, and this of course happens for every n larger than or equal n0. Okay, it is basically sufficient to see what happens. Remember that we are dealing with the limit as x goes to plus infinity, so we are just looking at the behavior of the function definitively. So if we have that an has a certain behavior definitively, well, of course, it turns out that f of x is of type 1, 2, 3, and 4 for every x larger than or equal to this and 0. So again, we can say that the function definitively has exactly the same behavior. So that implies that has the same limit for x that goes to plus infinity. Okay, let's now starting apply this criterion and see this in practice. Let's go to the example 2. In this example 2, we need to find the limit as x goes to plus infinity of 1 plus 1 over x, all raised to the x. Okay? Which of course is something that reminds us of the limit as n goes to infinity of 1 plus 1 over n to the n equal to e, right? So we know this limit, so we want to use at some point, okay, this sequence. And as always, we need to build an inequality, okay? And so we can say right at the start that we would expect, no, that this limit is going to be e. We are not quite sure about this, but this seems a reasonable idea, right? It seems a reasonable prediction. How can we prove this now? Okay, so the thing is this, that we need to build the inequality. An inequality where we have 1 plus 1 over x to the x in the middle, and now because this is gonna be a convergent function, a function that will converge to a limit, this will be in between two sides. Okay, there will be a right side of the inequality and there will be a left side of the inequality. And on the right side and on the left side we need a sequence of which we know the behavior, basically, right? Okay, so let's start with the term on the right hand side of the inequality. And of course we want to build a term which reminds of this sequence, but a term that we know is going to be larger than this. And we're doing this for x that belongs to each interval n plus 1. Okay, so we are considering now x in that interval, and remember that this implies two things. This implies that x is going to be larger than n, and that x is going to be less than n plus 1. Now, how can we build on the right hand side a sequence which is larger than this? Well, we can keep 1, right? And instead of using 1 over x, well, we should put something which is larger, for example 1 over n. In fact, we know that x is larger than n, which implies that 1 over x is less than 1 over n. Okay, but instead as exponent we will replace x with n plus 1, and we know for sure this is going to be large. Okay, let's do the same on the left hand side. we can live with this one, but this time we need something which is smaller than 1 over x, which implies something that instead of 1 over x we can replace 1 over n plus 1, because we know that n plus 1 is larger than x. And then we can just leave as exponent something which is smaller than x, for example n. And now we are happy because clearly, let me bring this to the right now that we know this. Okay, so what we can see here is that immediately we realize, and we will prove this, but we can say that this is clearly something that will tend to e, okay, to the Euler's number. This as well will tend to e, and as a result of this, by the squeeze theorem, the function which is in the middle will also converge to e. Now let's prove that both the left hand side and the right hand side will converge to e. Okay, so let me start by proving let me start with the right hand side. Okay, so what I want to prove now is that 1 plus 1 over n all raised to the n plus 1 will tend to e. Okay, but I can write this as 1 plus 1 over n raised to the n times 1 plus 1 over n. Okay, and clearly we know that this will converge to e, because this is one of the fundamental limits. But look at this, we know that as n goes to infinity, this term 1 over n tends to 0, so this will tend to 1, which finally proves that this will indeed tend to e. Let's prove now that the left hand side tends to e as well. So we want to prove now that 1 plus 1 over n plus 1 all raised to the n will tend to e. Okay, let's see how we can prove this. Well, we can say that this is equal to 1 plus 1 over n plus 1 all raised to the n plus 1, and then we multiply by 1 plus 1 over n plus 1 to the minus 1. In fact, if you do the product of these two terms, you will find exactly the left hand side. Okay, but now what we can say is that once again, as n goes to infinity, n plus 1 goes to infinity, so this term on the right hand side will tend to 1. And if you just make an easy change of variable here, and you say, for example, that m is equal to n plus 1, clearly you see that this limit is once again e. So this finally proves that also for the left hand side we have e as the limit of the sequence. Alright, so and this will conclude the proof, right? So we were able to prove that this sequence 1 plus 1 over x all raised to the x has e as a limit as x goes to plus infinity. So somehow this is just the real version of the sequence that we had on the right hand side. Okay, we can say in general that there is an observation here in order. So observation, if in general, if we have that a sequence an tends to a limit L1, also an plus 1 tends to L1, this would have simplified a lot our proof, because clearly whatever happens at n, it will be exactly the same if you just replace n with n plus 1. Okay, so let's move now to a new limit. We will now prove one of the fundamental limits that we know are the milestones for the calculation of all the limits. We will prove now that the limit of sine of x divided by x as x goes to 0 is equal to 1. Remember that last time we gave these as the other fundamental limits without proof. It's time that we give the proof now. Okay? Now let's start with the proof of this result. Now let's start by noticing that sine of x divided by x is an even function. What does it mean to be even? It means that sine of minus x divided by minus x, because of the property of the sign, we know that this is nothing else than minus sine of x divided by minus x, but this is exactly equal to sine of x divided by x, which proves indeed that sine of x divided by x is an even function. But if this is the case, the only thing that we need to prove at this point is that we can just restrict our attention just to the positive x, and we know that x will tend to 0 from positive numbers. Okay, so we will consider, in other words, we will consider just this part of the unit circle. Remember that this is 1. Okay, and we will take the limit of sine of x divided by x for x that is basically a positive angle approaching 0 from above. Okay, and let's say that we consider this as the arc. Okay, so this is x. X is gonna be exactly this, right? The arc that we are considering, and we are gonna now build the sine of x, which is this red segment, sine of x, and we also build the tangent of x, which is this other segment, and we can now write the inequality from the inequality. Sine of x less than or equal x less than or equal tangent of x, which is evident from this. Okay, so what we're saying is that the sine of x, which is this segment, is less than x, which is the arc, which is less of the tangent of x, which is the segment on the tangent taken exactly at the point 1, the vertical tangent, right? So we can definitely write this inequality. And now, of course, this is valid for x that belongs to the interval 0 pi over 2, because we said that we want to just consider positive arcs that will approach 0. So definitely we can say that x belongs to the interval 0 pi over 2. But if this is the case, that implies that sine of x is positive. So if sine of x is positive, we can divide all the terms of the inequality by sine of x, and we get 1 less than or equal x divided by sine of x less than or equal. Remember that tangent of x is sine of x divided by the cosine of x, but if we divide by sine of x, the only thing that we get is just 1. So we have this new inequality. Remember that this is because sine of x is larger than 0 in this interval, so the inequality still holds with the same signs. And now we take the limit as x goes to 0, but we see that this will tend to 1 because we know that cosine of 0 is 1. This, of course, is a constant, will remain 1, and by the squeeze theorem, once again, we see that this ratio 1, which finally proves, that the limit as x goes to 0 plus of sine of x divided by x is equal to 1. But because we know that this function is an even function, we also know at this point that the limit as x goes to 0 minus of sine of x divided by x is equal to 1, and we conclude that limit as x goes to 0 of sine of x divided by x is equal to 1. Okay? So this will conclude the proof. Let's move now to another of the fundamental limits that we have introduced in lecture 17. And let's take the limit as x goes to 0 of 1 minus cosine of x divided by x squared. We know that this is 1/2. Okay, so we want to prove this limit now. We want to prove this result. Let's provide the proof now. Okay, so we can say that the limit as x goes to 0 of 1 minus cosine of x divided by x squared, okay, this is just equal to the limit. Nothing changes if we repeat exactly 1 minus cosine of x divided by x squared, but then we multiply and divide by 1 plus cosine of x, 1 plus cosine of x. I can do this, nothing changes, and this gives me limit as x goes to 0 of 1 minus cosine square of x divided by x squared times 1 plus cosine of x, right? But this again can be written as limit as x goes to 0 of sine square of x divided by x squared times 1 divided by 1 plus cosine of x. But now look at this. Remember that this is nothing else than the square of sine of x divided by x, which we just proved to be something that tends to 1. So this will tend to 1. And when x goes to 0, cosine becomes 1, so this will tend to 1/2. So this finally proves that this limit is indeed 1/2. Okay? Let's prove another limit now. Let's take the limit as x goes to 0 of tangent of x divided by x. And remember that this limit is equal to 1. Okay, we want to prove that this limit is indeed 1. Okay, let's give the proof now. Proof. We can write limit as x goes to 0 of tangent of x divided by x. But we can write this as limit as x that goes to 0. Tangent of x is what? It's sine of x divided by cosine of x. So we can write this in this way, and we know now that this goes to 1, this goes to 1, but this is then equal to 1. and then it's easy way of proving this limit. Another fundamental limits was these limits. Limit as x goes to 0 of arc tangent of x divided by x. And we want to prove that this limit is 1. Okay, let's provide the proof then. Proof. Now, for this limit, we can make a change of variable. So let's set y equal to the arc tangent of x, which implies that if we apply the tangent function to both sides of this equation, we get that the tangent of y is equal to the tangent of the arc tangent, which is nothing else than x. Okay, so we have this new equation that x can be replaced with the tangent of y. Not only this, we also know that if x goes to 0, then also the arc tangent, which is y, goes to 0. So we can now rewrite the given limit as y goes to 0. Then we have a fraction. Instead of the arc tangent, we will write just y, and instead of x, we will write tangent of y. But this is a limit that we know already, right? We know that this limit is going to be 1, so because of the previous proof. So this already proves this other statement. Now, no wonder that if I want to prove that the limit of the arc sine of x divided by x as x goes to 0, well, this is going to be 1, but clearly this is exactly the same proof, right? Because what can we do with this proof? Okay, let's do this by exercise. We can just set y equal to the arc sine of x, and then applying the sine function, we have that the sine of y is equal to x, and we know that if x goes to 0, y goes to 0. So this becomes the limit as y goes to 0 of this fraction. Instead of the arc sine of x, we'll write y. Instead of x, we will write sine of y, but we know that this is equal to 1, and this is an easy proof to do, right? Okay, so let's move now to another limit that was in the list of the fundamental limits. Limit as x goes to minus infinity of 1 plus 1 over x all raised to the x, which is clearly just another version of this limit that we have evaluated, right? So the only difference that we have now is that instead of having x to plus infinity, we have x to minus infinity in these new limits. Okay? So how can we prove these limits? How can we prove that the limit as x goes to minus infinity of this 1 plus 1 over x all raised to the x is indeed equal to e? Because this is the thing, right? We want to prove this. Now, we can make use of the previous limit by setting, okay, if we set y equal to minus x, okay, well, that implies that when x goes to minus infinity, we have that y goes to plus infinity, which is good because it is somehow getting closer to the previous limit. So now we can rewrite the limit as follows. Limit as y goes to plus infinity of 1 minus 1 over y all raised to the minus y. Okay, so now the problem is how can we rewrite this term. Okay, so let me rewrite 1 minus 1 over y, all raised to the minus y, as follows. Okay, let me first make a common fraction. So we have y, and then we have y minus 1, all raised to the minus y. Okay, but this is nothing else that y divided by y minus 1, all raised to the y. All raised to the y. Good. And now we used one of those tricks that we saw last time. We can write y as y minus 1 plus 1. Okay, nothing changes. And this can be rewritten as 1 plus 1 divided by y minus 1, all raised to the y. What we need to do now is basically having an exponent which is just equal to this y minus 1. So we put the minus 1 here, and then we multiply by y, 1 plus 1 over y minus 1, all raised to the 1. Okay, this is exactly the same. We have a few other fundamental limits to prove. In particular, we want to prove the one related with the logarithm. So let's first observe that the function logarithm of x is continuous, and it is continuous because of the meta theorem that we didn't prove, but we have already used extensively. Okay, so with this in mind, let's first observe that one of the limits that we have proved is namely the fact that limit as x goes to plus infinity of 1 plus 1 over x, all raised to the x, is equal to e. Well, if we now apply the logarithm on both sides, we have that the limit as x goes to plus infinity of the logarithm of 1 plus 1 over x, all raised to the x, this is equal to the logarithm of v, which is just like saying that limit as x goes to plus infinity of x times the logarithm of 1 plus 1 over x is equal to 1. So this is a first important result. Okay, so let me use this result, let me call this A. Okay, I will put this, let's say that we have this first result. Okay, the limit as x goes to plus infinity of x times the logarithm of 1 plus 1 over x is equal to 1. In a similar way, we can prove a similar limit for x that goes to minus infinity. For that, we need to use the fact that x goes to minus infinity of 1 plus 1 over x raised to the x. This also converges to e, and we have just proved this. So again, applying the logarithm on both sides, we get limit as x goes to minus infinity of the logarithm of 1 plus 1 over x, all raised to the x, is equal to the logarithm of v, which in turn means that the limit as x goes to minus infinity of x times the logarithm of 1 plus 1 over x, this is equal to 1. And this is another result which which we call b. And now, by a simple change of variable, and the change of variable is if we set y equal to 1 over x, we have respectively from a we can basically obtain another result which I'm gonna call a prime. And remember that if we have that x goes to plus infinity, of course this implies that the y tends to 0 plus. So the a result, okay, the fact that the limit as x goes to plus infinity of x times logarithm of 1 plus 1 over x is equal to 1, then this gives limit as y goes to 0 plus of, instead of x, I'll just use 1 over y, and instead of the logarithm of 1 plus 1 over x, I have 1 plus y, which we know at this point that is equal to 1. I can just rewrite this as limit as y goes to 0 plus of the logarithm of 1 plus y divided by y, and we know at this point that this is 1. Okay, so this is a prime. Now, using b, we can get b prime. Because x goes now to minus infinity, well, that implies that y will tend to 0 minus. So we have that the limit as y goes to 0 minus of 1 over y logarithm of 1 plus y, again this is equal to 1, which gives that the limit as y goes to 0 minus of the logarithm of 1 plus y divided by y, this is now equal to 1, and we can call this result b prime. And now, considering a prime and b prime, we can therefore conclude that the limit as y goes to 0 of the logarithm of 1 plus y divided by y is equal to 1, which was one of the other fundamental limits we gave in lecture 17. We can now use this last result to prove one of the other fundamental limits. We in fact want to prove now that the limit as x goes to 0 of e to the x minus 1 divided by x is equal to 1. Notice that this is another example of undeterminate forms, because if we replace x equals 0, we have 0 over 0. Now, how do we prove this? We can just set e to the x minus 1 equal to y. And well, that implies that if x goes to 0, then we also have that y goes to 0. And we also need to evaluate x from this expression, and with a little bit of manipulation we get e to the x equal to 1 plus y, which implies that x is going to be the logarithm of 1 plus y. I think you see what I'm trying to get from this manipulation, because in fact now we can rewrite the limit as y goes to 0 of, well, instead of e to the x minus 1 I will put y, and instead of x I will just put logarithm of 1 plus y. But this, because of the previous limit, we know that this is going to be 1. So this concludes the proof. Another limit that we had in the list of fundamental limits was limit as x goes to 0 of x times logarithm of x. And we want to prove that this limit is equal to 0. Okay? Now you see that in this case the undetermined forms that we have is 0 times minus infinity. Okay? Right, so to prove this we can set we can set x equal to 1 over y. And of course this implies that when x goes to 0 plus, in fact I need to make an observation here. Let me do this observation here. When we say x equal to 0, indeed this limit makes sense only for positive values of x, because the logarithm can only be evaluated for positive axes. So when we say this, we mean that x has to go to 0 plus. So this is the limit we would like to prove. Limit as x goes to 0 plus of x logarithm of x is equal to 0. Okay, so this is what we want to prove. Now if we have that x goes to 0 plus, y will diverge to plus infinity. So this implies that the limit is now limit as y goes to plus infinity of, instead of having x, we will just replace with 1 over y, and instead of having logarithm of x, we have the logarithm of 1 over y, which is equal to the limit as y goes to plus infinity of, by just using the properties of the logarithm, we simply have minus logarithm of y divided by y. And we know that this is 0 just because the power wins over the logarithm. We already know this, we proved this. So this concludes the proof. This concludes the proof. We can generalize this result. Okay, we can say that in general, we can say that the limit as x goes to 0 plus, in the previous limit we had x, but we can say that x to the a, okay, and this is for every a larger than 0. So any power of x multiplied by the logarithm of x, and we take now the absolute value and we raise this to b, and this is true for every b larger than 0, we can say that this is true in general. So this is equal to 0 in general. And of course this is just a consequence of the previous proof, when we saw that by that change of variable we ended up with a ratio of a logarithm with a power. So it is clear now how to prove this. So the proof is the following. If we once again set x equal to 1 over y, we have now that if x goes to 0 plus, y goes to plus infinity. So the limit is now limit as y goes to plus infinity of 1 over y to the a multiplied by the absolute value of the logarithm. Instead of x, we'll put 1 over y, all this raised to the b, and this is equal to the limit as y goes to plus infinity of now using the properties of the logarithm, we can rewrite this as the logarithm of y, because the minus has been absorbed by the absolute value, all raised to the b, and then we have y to the a. And once again, this is 0 because of the same reason, because once again we know that the power wins over the logarithm. And this concludes the proof.